And today's plenary session presents the global topic of water from two perspectives. We will have Dr. Bernhard Lehner, who will talk about global monitoring of terrestrial surface water, not seeing the lake for the rivers and trees. And afterwards, Dr. Jeff Hausman will present views on molecular vibrations of water, predicting global distributions of photosynthetic organisms across lakes and oceans. They will be both introduced by a member of our local scientific committee, Dr. Paul Di Giorgio from Université du Québec à Montréal. I'll give the virtual stage now to Paul. Thank you.
Thank you, Nona, and thank you. Congratulations to our Hutchinson recipient and for an excellent talk. And yes, my name is Paul Di Giorgio. I am from the Université de Québec in Montreal here in Canada and part of the scientific committee of this most excellent ASLO 21 virtual. And the scientific committee considered it was timely to have a plenary devoted to recent advancements and developments in general area of remote sensing and related fields. And this is an area that has had a lot of progress recently and major implications to inland waters and marine systems and so on. So in order to broaden the scope of this plenary, we decided to invite two speakers in order to highlight recent developments both in inland waters and marine waters as well, and in different fields, in different types of scientific problems. So today I have the great pleasure of introducing not one, but two outstanding plenary speakers. You can post questions and comments in the chat to both, and we will address them at the end of the two talks. So our first speaker is Dr. Bernhard Lehner. Bernhard's main research themes are large-scale hydrology, hydrographic mapping and modeling, and the management and conservation of freshwater resources globally. The research carried out by his group is at the interface between geographic information science techniques, remote sensing imagery, hydrology, watershed and landscape modeling, and climate. His group is dealing with what I think is one of the major challenges in contemporary aquatic sciences, which is the mapping of inland waters and the quantification and modeling of surface water resources at the regional and global scale. So Bernhard did his early studies in hydrology and geography in Germany and completed a PhD in the University of Frankfurt. He joined the Department of Geography at McGill University in Montreal in 2006 as professor in global hydrology. And he has established there since then a really active research group that has produced some of the most comprehensive and advanced cartographies, synthesis and modeling of surface water resources ever accomplished to date, of unprecedented detail and resolution. So the data products that this group has developed and rendered of public use over the past decade include the HydroLakes tool, which is used for estimating the volume and age of water stored in lakes globally, the Grand D Global Reservoir and Dam Database, the GLWD Global Lakes and Wetlands Database, and others. And more recently, the group has published a paper actually a couple of weeks ago in Nature for the first global cartography of intermittent rivers led by one of Bernhard's PhD students, Matthias Messenger. Again, another major contribution to our understanding of global freshwater resources. These tools and data products and models provide the necessary platform to explore a wide range of regional and global questions pertaining water resources. These questions include impacts of climate change and environmental alteration on water availability and quality, the fate of materials and contaminants in aquatic networks, the eco-hydrological effects of dam constructions worldwide, environmental flow requirements, and integrated freshwater management and protection strategies. There are many research groups around the world now routinely using and benefiting from these tools and data products, and from the underlying techniques and conceptual developments that Bernhard's research has produced over the past decades. In today's plenary, Bernhard will be sharing with us some of these developments and some of the opportunities and challenges that lie ahead. Bernhard, the floor is yours.
Thank you so much, Paul, for the very nice introduction. Let me ask everyone struggle through screen sharing first. Good, I hope you see that. Yes, it's quite an honor to speak to you all virtually at ASLO in Mallorca, right? The only thing in the spirit of Mallorca that I have preserved in the Zoom meeting is that I'm sitting here with my shorts on. Other than that, you hear me out of my Canadian home office. I hope that's not too depressing for this island meeting. I've been asked to speak about global monitoring of terrestrial surface water, because that's what I do for many years now. And maybe first I should point out, it's not only me. I put there just as a casual with many students and collaborators. The list is so long, I never know where to start, and I never can really do them the real gratitude that I should give them, because this is not a one person's job, that what I can show you now. And I should also do one other thing and use this opportunity and start with an apology. Many of you might know me in person, or more likely by email or sending a request for data, something like that. Your email might still sit in my inbox for a day or a week or a couple of months, or maybe even a year. If you're a very optimistic person, you might hope that you still get a reply from me, which I'm really trying to do. But I thought I should say that once I know that I'm very difficult to reach. This is part of what I do. Creating data comes with a caveat of lots of users who want the data and have questions about it, which is fantastic for me to see. There's nothing that makes me more happy than sharing the data and seeing it put to good use. But yeah, if you haven't heard back from me, hang in there. I'm trying my best. But with that, let's start and see why I gave this talk the subtitle, Not Seeing the Lake for the Rivers and Trees. I'm trying to focus a bit also on the difficulties of mapping what I do, global lakes, global rivers, also wetlands. Here's just a starting slide reminding you of all the different shapes that lakes come in. I could do the same with rivers. You know that in principle. What I'm heading for with this opening slide is to remind everyone that lakes, when you look at them globally, they're really very different. Some of them, maybe here the Beaver Dam at the bottom, a very ephemeral lake. Would you even put that on a map, or would you assume maybe it's gone again in a year or two? So that's where problems start, that we have to handle on a global scale over vast areas, very different types of lakes, very different dynamics. So this is a human view of the whole thing, photos, the way you would see it mostly. This here, courtesy of one of my PhD students, and a way of seeing it based on remote sensing imagery. It's actually super high resolution imagery, 30-meter pixels. We can do that today. And we can create the outlines of lakes as we know them. Even an advantage, you see not too much, but some red colors, some blue colors in Tibetan lakes. Where we can see, did these lakes grow or shrink over time? This is very difficult to rebuild with a more old-fashioned paper maps or something. How would you put that information on it? Remote sensing has that capability for us to do, but it comes with caveats, and it's not a no-brainer either. How can we do this? Can we do this everywhere? A couple more photos to set the stage of where I think the difficulty really lies. Simple question, is that a lake? I can't see your faces now, so let me assume you all nod on this and say yes. Easy case, looks like a lake, feels like a lake, without going into definitions, what actually makes a lake or makes a lake different from a pond or a wetland. Maybe more difficult, now it depends a bit on who you are and what you want to study. Is that picture showing what, a wetland or a wetland mixed with lakes, or maybe it is a lake that is just in a dry state? Here's another version of a more difficult object, if you want. Is this one lake? Is this in the flood season at least, or connected, or maybe never? It will depend on the species you study or what you study. Biogeochemical cycles, are these pools connected? Should we represent this on a map as one polygon, one unit, or in raster and grid format, it would be disaggregated into pixels anyway, but should we try and find ways to say these are connected, these form one water body, or are these multiple ones? These are huge challenges in putting water on a map. Here's another one. This is somewhere in northern Siberia, another remote sensing image. Cryogenic formations of freezing, thawing, give you all these patterns. And the question here that I put on the top is, where does the lake end and the river start? What forms part of the flowing water body? What is standing? Does it even matter? Do we need to make a lake end and a river start? There were many presentations, I think, in the ASLO meeting where the argument is made. For certain processes, yes, we should treat them differently. For others, maybe not so. What about features and objects like this? If you look at this from the top with remote sensing imagery, what you would see is a water surface surrounded by a ring, surrounded by water surface. First of all, is this a lake or is this some human generated water body? Do we want to separate this? Often we do. But even if we treat it as a water body, is this a lake within a lake within a lake? Should we remove the boundaries? Should we treat it combined? Very difficult. I can do this endlessly. Here's one picture shows a lake, the other shows the Amazon River. So here maybe this distinction is not the size. Even if you say lakes are bigger or rounder than rivers, whatever you want to pick, you will find examples why that doesn't hold. Here might be it's flowing versus standing, but that is very difficult to measure with remote sensing imagery. Maybe the answer, the bottom one is the Amazon, the top one is a lake. If that was too difficult to guess, I don't know, here's an easier one. One is summer, one is winter, which one is which? I hope you get that one. This is really the exact same location, just where I live. Why do I put that image up? Because satellites in the winter will struggle to see the water surface and measure dynamics in the winter because it's under snow and under ice. So we have to use very different imagery to do that. And that might be something maybe to those of you who make work possibly in the tropics, exclusively in regions where that is no issue on a global scale. Our methods that we apply have to work both in the tropics, in the north, under snow, under all weather conditions. Good. I have split my short talk into 3 parts. The first one I call the human intelligence approach of how to map this. I do that a bit intentionally and controversially, maybe, I don't know, to make it distinct from the artificial intelligence approach that I use afterwards for more remote sensing. Human intelligence is something that I used a lot. That's where all the students come back in, a lot of manual work. So we often actually go back and try and find old-fashioned maps, paper maps, not necessarily in paper format anymore, but digitized versions of it. Like this has been already mentioned, the HydroLakes database, about 1.4 million lakes that are larger than 10 hectares, is a conglomerate of existing data sets that we didn't make from scratch, but we tried to combine it. Here's the Canadian example, a really fascinating, very high resolution polygon map that was made over time by many researchers, the government, pulled it together for all of Canada, so you can zoom in higher and higher resolution. It's really very detailed. So why don't we use that everywhere globally? Is then often becoming the question. Because of issues like this. Here's a zoom to the delta of the Mackenzie River up in the north of Canada. And that's how we got the map there. Despite its high quality, polygons of rivers and lakes were one unit. They were contiguous. That's a very typical thing that paper maps have, that issue that is often not a separation between those water bodies. So what we did is manually split that, go in, cut these polygons open, remove the rivers because we were interested in lakes. And what you see is what's left. Once that's done, it's a very unique map. because this is the first time, although not everything's left, where lakes are isolated and you can call them lake, functionally or structurally a lake. At the same time, you see, we might have missed a couple of the oxbow lakes from the bigger river because there's a limit of what you can do as a human. It's very time intense to do this. It took us a couple of years to clean up data and then merge it. And that's where this comes in then. The artificial intelligence approach as the maybe solution to it all. Will remote sensing save the day? Whatever I say in the next slides is, I'm a big fan of remote sensing. So don't worry, yes, in some way, I hope it will save the day. But there's quite a few caveats that I want to highlight of why it won't be a quick solution, in my opinion. Here's a set of remote sensing images that all show some pieces of water bodies somewhere in the world. That's great. We have remote sensing imagery now everywhere. All kinds of satellites and sensors are up there. This is great on the one hand. On the other hand, as simple as water is for your eye maybe to distinguish here, you see it, but you also know a bit more, you know, the structure of how this should look like. If you are just a satellite, or if you only analyze the frequency that you get back, is actually really tricky to separate water from other surfaces. The colors in this case would be all different based on chlorophyll and on suspended solids that are in the organic matter, the satellite sensors, and also errors and issues like atmospheric distortion that gives you different images at different times. So on the one hand, it's great that we have lots of sensors and variability in spectral signatures that we can utilize to our favor and distinguish different types of lakes maybe. At the same time, it gives us endless opportunities to do this incorrectly. Misclassifications are a prominent feature. And last one is not to forget, we always like to show you the good pictures and hide these ones. There's also, we have 40 years of remote sensing imagery, and from day one to today, we have issues like this. They are not all clean and clear. And it's not even natural things necessarily like clouds, it's just technical issues and errors and glitches that are in the data, and we have to filter all this out to get clean images at the end. Even if the data is correct, time plays a role. Here you will see 4 images now. This is for also in Canada, the Algonquin Park, a Sentinel-2 image through 4 seasons provided by one of my PhD students. So this is spring, then you go into summer, and then there will be fall and winter. It's not only the colors change, the whole signature changes. If you run an algorithm on this to detect where are the lakes, like especially this is really striking in winter, it completely changed. Now you would like to detect the white pixels, and in the spring and summer it was the black pixels. When do you flip that? So you kind of have in parallel to run a climatology model if you want to still run the same algorithm over the same scene throughout all the seasons. Really challenging. Here's another problem with remote sensing imagery. On the left is a very high resolution global image of transitory water surfaces, so pixels that are not always underwater, but where in this case it's based on Landsat imagery, optical satellites see occasionally water at 30 megapixel resolution. So great data set. I show that even a bit more. On the right side, you see a different product from a different, actually multi-satellite product, different images, including, and that's why it's so different, using radar instead of optical sensors. It's called Teams D3, also 90 meter, showing you in principle the same thing, but you see it in the colors already. It shows you much more, nearly triple the amount. Why is that? Why do some satellites see more than others, although they look for the, again, in principle, at least for the same thing? Here's one reason. That's why I had that in the title. If you have your water surface, lake or river, or whatever it is, under trees, most satellites have real huge problems seeing that. The optical ones, you can't see it at all. The radar have an advantage there. You can, with certain angles, you can see a little bit underneath the canopy, but also limited. It's not only canopy alone, also vegetation on the lake make it very difficult to see the water that's underneath. That's why we get very different global estimates that come from satellites that have the same goal. Here's an image that I really love for it really shows how dynamic rivers are. This is a imagery that was pulled together from 32 years of Landsat imagery and shows you, this is the Brahmaputra River, all the meandering and how it even shifts a little bit in its course and creates new meanders over time. How should we map this? I mean, you see that we can map it in an animation, but how should we put this on a static map? Should we even put it on a static map? I think we should, in part because we would all struggle with handling this type of information. It's super big data sets, are also really complex to analyze. So we do try and put it back into a static map in the first place. How is it done? That has been actually, I think, really tremendous improvements over time. This is one product that came out only 1 or 2 years ago, 30 megapixel resolution, where seasonality is here color coded on the right. How often is a certain area flooded? How regularly is it seasonal? Is it infrequent? Is it ephemeral? And those give us really, really great new products. This is another product, Global Surface Water Explorer, bit longer time series, very similar data. And you see in different colors, different seasonalities of what we can see. And all of this, again, high resolution imagery. But no matter what, this question remains and stays and doesn't want to go away. If you want to separate rivers from lakes, we are still struggling because both rivers and lakes tend to be permanent, for example, and that alone is no distinction. And if you look at them, how dynamic they are really difficult to treat. Some of them fluctuate every year. In the Tibetan Plateau, it seems to be over longer time frames. They keep growing, others dry out. And then you have on the right top a new dam that comes out of nowhere. Suddenly there's a water surface. How, again, should we put this on a map? Should we put one polygon around this whole object? Or should we even attempt to figure out which pixels are connected? All these are challenges that even remote sensing cannot easily answer for us. So I've made a short list of what's good, what's bad. Maybe at the moment with remote sensing, sensors are improving, resolution in time and space is improving. Sensors, we have new ones that can detect new things that we haven't done, or we combine them into multi-sensor approaches. They're particularly great to map extent and altimetry of water bodies. They tend to be increasingly free, which is great. We have fast processing and really intelligent artificial intelligence, machine learning techniques now that we let loose on this data with tremendous new results. But as mentioned, we still can't separate individual water bodies, characterize them perfectly. We can't see underneath vegetation. And maybe the biggest problem that I see, what we often forget in the enthusiasm about remote sensing, good enthusiasm, is even the oldest remote sensing goes only back to the 80s. And particularly the new sensors, the super exciting ones that are better than those before. The SWOT mission goes up 2022 with highest resolution, extent, and altimetry measurements expected, but the data will start in 2022. And going back in time remains a problem for all this. And that leaves me with the last piece in this very fast talk. I hope I'm still in time here. Mixing all the information, human, artificial intelligence, remote sensing. There's exciting projects like this. 2 years old, Allen and Pavelski mapped large rivers. They had to be more than 30 meters wide, but they started off with remote sensing imagery and then improved it through manual corrections. They went through multi-year efforts also to actually distinguish rivers from other water bodies, and then they declared them rivers. And now we have a map where you can go in and say, that's my rivers. We have done the same with lakes. We have done the same with wetlands, where we merge and curate the data, bring different data sets together. This is the infamous today Global Lakes and Wetlands database. It's nearly 20 years old. If you have a chance, I'm the author on it. So I have the authority to say, if you don't have to, don't use it anymore. We can do better, but it's still a very consistent product. Good news, we're just working on a revision of that with higher resolution and better information, hopefully coming out by the end of the year. Another product we made by merging information from remote sensing imagery, model approaches, statistics is HydroSHEDS that many of you use, where we create catchments and river networks. It's also good news, there's also a new version 2.0 in the making, which covers also the north. This is Iceland. And I show you what we do is we turn elevation into river networks and combine that then with hydrological models to get quantities of river flow. And the more you combine information, the more you can do. This is out of the HydroLakes database. Again, it was combined with elevation data to get at lake depth and volume. We're now working also for HydroLakes to get temperature regimes, seasonality of temperatures from other remote sensing imagery for every single lake, all the 1.4 million. These are all PhD chapters from students of mine. This has been mentioned before, and there was a talk at ASLO about this, merging in hydrology to map intermittent rivers. About 30 million kilometers of river reaches we have mapped now, and combining it with discharge and hydrology information, we can get a seasonality. And maybe the future, we are also working on combining it with water quality, in this case, wastewater, where wastewater treatment plants, what happens downstream of those by merging in other models. So with that, I'm kind of at the end with one last outlook. So I showed you all the way. We came really far. We can map 30 million kilometers of rivers today. We can map 1.4 million individual lakes. And we're now working on enriching that with all kinds of information from all kinds of models. So this shows a map in the what we call now Hydro Atlas database, showing you catchments. And I just picked one variable. We have over 50 of those hydroenvironmental variables. That's elevation per catchment. I can transition that to elevation for every river reach in the world. And the last one, maybe the most exciting for some of you, is just in the making. We do the same now for lakes. So this is for every lake. It's elevation. And again, there's 50 more variables to come, also hopefully coming out at the end of this year. And with that, I'm at the end. Change the title here a little bit to, yes, I think we made exciting progress with remote sensing and water surfaces, but there remains much to be done. Thank you for listening.